software engineer here in Utah. I've been using Go for a couple of years and had the chance to go to different conferences and things like that. And I just thought it would be I had a good excuse to sign up to do a talk on runtime, and that would like force me to learn a little bit about it. Go is a really interesting runtime compared to other languages because it does a lot of unusual tricks that aren't really that common, like escape analysis and stack allocation in the way that it does, like it's routine stacks and a few other things that we'll get into. So that's why I thought it'd be fun to talk about. And also, if you do much like heavy performance-related stuff with Go, like it's nice to have some tools to reason about what the code is doing, why some things don't work, or why you might want to change things. So who here gets to write Go at their job? That's awesome. That's a ton of people. Out of those people, like who actually has to do a whole lot of like performance tuning? Yeah. All right. That's good, right? I mean, if it's fast enough, it's fast enough. Why waste the time? All right. So this will definitely, I hope, help some of you guys. Oh, this is gone. Great. 1 second. That was my computer's subtle way of telling me to get on with it. I think it's cycling through. We've got to be next on it.
There it goes.
Yeah. Great, we're back on track. All right. So for those of you who don't know, it sounds like almost everyone here does, but we'll just keep the spiel. Go is an open source, compiled language, or rather, Go the language is, there's just a reference that anyone can implement, but the most common implementation is the compiled one. There are some crazy Go implementations that run on anything from the Node.js VM to the weird one that kind of runs on the Java VM. I don't know. They showed up on things a while ago. But for what we're talking about, when I say Go, I mean the Go implementation that's defined by I believe it's called the GC toolchain. So it's the main one. But yeah, it's all that stuff. I should have looked at this every time. So yeah, it's all that stuff. It comes from Goop. It's basically the whole point of Go, the sweet spot, is really around concurrent network programming. It does a lot of other stuff well, but that's kind of what it was built for. Serving search queries and fun stuff like that. I already went over that, didn't I? All right. So I had to think a little bit because I was afraid someone was going to call me out on if I said something that happened in the runtime, it wasn't really the runtime because it's kind of a fuzzy term. If you run Python, maybe the runtime is the C Python interpreter. If you're doing Objective-C and we're talking about ARC, on the reference panel, I might talk about that as part of the runtime, but those are compiler inserted calls. So this is just stuff that happens that basically you didn't write or import as a library. And I'm sure I can skip through edge cases, but that covers most of what I'm going to talk about. It's all magic. And I've mentioned that as well. True to form, I always do this. So anyway, we'll talk about the GC toolchain. Which, do you guys know what I talk about when I say the GC toolchain? It's what's invoked by default if you run Go build. So it's just normal Go. You can also run go build dash compiler with GCC Go or whatever, and use an alternative toolchain or whatever. And also, almost all the things I'm saying in here, you just have to, in your head, add this sentence onto the end. It's when I say it works this way, it's unless you're using unsafe. The unsafe module breaks most of the guarantees and the things that Go gives you. So, what does it actually do? The big one, of course, by people who go runtime is garbage collection. And the Go garbage collector is crazy, and it was hard to decide which garbage collector to talk about because they're very actively working on one in Go 1.4 plus, I guess. It's super crazy. We're going to mostly focus on the current one since that was the source code I had access to. So that's the one that everything I should say should be fairly accurate with respect to that. You get all kinds of like balance checking. So Go is like a safe language in the fact that like you can't access memory that it's garbage memory, for lack of a better word. So that means when you have like arrays, which are really the only place where like implicitly corner arithmetic is known in Go, then you have balance checking. But that goes with arrays and slices, essentially. Although it's certainly possible for the compiler to occasionally be smart enough to line balance checking. I really like Eli. I didn't hear Eli used a whole lot until Go got popular. Now it's being used more often. There's also like various cool runtime stuff like that comes into play when you're like dealing with like what used to be called duck typing, you call structural typing, because you could check at runtime and see if some arbitrary type implements in the interface. There's all kinds of reflection tables. And I called out part of the runtime and all the stack management for Go routines, which is pretty cool. That stuff. And the scheduler. The scheduler is another like huge piece of the runtime along with the garbage collector that has a huge impact on the performance of your code. Since Go uses lightweight threads, you basically end up with a user space scheduler rather than letting the kernel do all the work, although it does certainly some of the work. So you have to make your own scheduler, and that's pretty hard to do right. And in general, like what they call cooperative multitasking is really hard to do right without getting into like starvation. That's why if you have like something like Node.js, it's not that hard to block the event loop by accident. Or, and this was I think before my time, but OS 9 wasn't that hard to like tweak it down if you didn't do it. I found this really awesome like quote that's stuck with me for a few months. You guys ever looked at like Raven Chen's blog? The old new thing. He's like a Microsoft lead guy. He writes awesome stuff. He has an awesome way of building a garbage collection, which is, let's read it out loud. It's a way of simulating a computer with infinite amount of memory. The rest is mechanism. And the reason that's an interesting way to look at garbage collection is because basically assuming you have like an infinite amount of memory, you could use a null garbage collector and just always ask for more memory and never reclaim it, and that would be a valid way to do GC. And where that comes into play is that there's not necessarily any guarantees in a lot of garbage collectors that your destructors will ever run or that you'll know when they run. And this quote kind of points out how that's true in my mind. It's a big thing in Go because they do have the concept of destructors kind of in a weird way, but they're not really guaranteed to work. So probably never want to use them. Just play it safe. Don't touch them. There's a bunch of like keywords that go along with garbage collectors, so if you're familiar with it, it's non-copying. And what that means is, as programs allocate memory and like free memory, or as the garbage collector does that, you can end up with like holes in your memory. You know, one object got deallocated and it's sitting between two live objects. A copying GC can like move that around and compact it, and Go doesn't do that because that requires a lot more cleverness, especially in a language that actually has pointers like Go does. You have to adjust all the pointers. Although, interestingly enough, Go does do a little bit of copying, like when they do their stacks now. So they do adjust pointers on the stack, which is pretty crazy. Non-generational. So Go's garbage collector is actually really young. It just hasn't happened in years that something like the JVM or the .NET runtime would have put into it. And what most of these more advanced GCs end up doing is like sort of generational thing, which works out the heuristic that most memory that you allocate you get rid of quickly, probably something like local variables, and then the rest of it lives forever. And that's kind of the heuristic that's based on. So you often will hear things like the EDA generation or promoting to a more longer generation. Go doesn't do any of that yet, as far as I know. It's also STW, which I don't know this acronym. I knew the meaning of it, but I didn't know this acronym until recently, so that's Stop the World, which is basically what it sounds like. When the program's doing garbage collection, it's a lot easier to do it if stuff isn't changing concurrently. So the Go 1.3 garbage collector is Stop the World. Interestingly enough, the Go 1.4 garbage collector that's not as true. It's still partially true. And they do some work in parallel. And the precise piece is actually really cool. Let's see if I have a thing on that. I did too. So Go's garbage collector is precise in that there's two types of GCs, conservative and precise. Conservative GCs are easier to implement because they don't require as much integration with like the runtime. The most famous one I know of is the phone GC that people will sometimes use for C. And basically what it means is if it looks like a pointer, it won't free it. So periodically, that GC will look at all the memory you have that it's allocated, and it will see if it looks like there's a pointer to something that's alive. And if it finds, a pattern of bits that looks like a pointer, it'll pin that object in memory that won't get deallocated. It's the easy way to do it, but there's some problems. Now, the 64-bit system isn't as big of a deal because the odds of finding a random sequence of bits that correspond to some memory you've allocated it's a 64-bit pointer are not really that high. But in a 32-bit system, it can be a big problem. And that's why for several years, Go was not really a good option on a 32-bit system. It worked, but you always knew that something weird might come into it and you die. You really predict if that would happen very well. So we just had to steer clear of it. When I was at Space Monkey, that was a big issue because we were writing code on an ARM device. If you followed me in your blog post, they've since changed from Python to Go on the ARM device, and that's, I assume that's because the 32 or because the GC is now precise. I'm sure there were other reasons. I can tell you this reason why they didn't do it originally, though. Issue 909 is actually the second most starred issue on the Go issue tracker ever, and I think it was closed 2 weeks ago, and that was when they made the garbage collector fully precise. I just saw it come up on Twitter just barely. It was pretty cool. But really, for the last year, it's been close enough that you could use it on a 32-bit system. Most people think, 32-bit, who cares anymore who has 32-bit systems, but Go 1.4 is going to support Go on Android, so it becomes relevant once again, at least until all of our phones are 64-bit, which will probably be 2 years or something, I don't know. I know they have some 64-bit ARM processors now. So yeah, that was a big deal. It's done now. It's precise. One really cool thing that makes Go's garbage collector a little different than most languages is, this is hard to say because there's lots of ifs, ands, and buts, but on something like the JVM, almost everything is going to be allocated on the heap until you take into account crazy runtime jet stuff and lots of other things. And because of that, it just makes it harder. It's not really as fast as allocating things on the stack, and having to box every type also poses a significant penalty. So Go has true value types, and they actually are able to, through escape analysis in a safe way, allocate stuff on the stack, which means certain local variables to your functions won't get promoted to the heap sometimes, and sometimes they'll be really, really fast, which is awesome. So it's just a really nice performance win without having to, spend 1 bajillion man-years on your JIT implementation, Science had to do now Oracle. They've got there. The JVM is really fast, but they had to work really, really, really hard to get what Go kind of has for free, just by the fact that they can allocate data on the stack. And anytime that data that you've allocated on the stack, which you can do that in C really easily, allocate data on the stack, you just can't use it afterwards after you return from a function because it's gone. Go can really just automatically promote that value to the heap. And Go does support finalizers, even though they don't really talk much about it. There's a package, or in the runtime package, there's a set finalizer call that you can use to basically implement object destructors. And it's generally used most often, I think, with CGO, but other than that, it's very unidiomatic to use it. It's more idiomatic to use things like the defer statement for resource cleanup and RAII sort of stuff. Excuse me. Okay, so I'm going to talk a little bit about the crazy 1.4 GC. I tried to write out what it would do, but it took too much, so I just figured I'd talk about it. There's all the Go plans, essentially design docs and stuff are available. They pretty much just put them in Google Docs and link to them from the website. So yeah, I feel like they're trying to cross-sell a product there. Who puts their design docs in Google Docs? Anyway, they have some really cool ideas. One of the biggest criticisms that I see like leveled against Go is it's not really real time, so it's not really a systems programming language by that definition of systems. And kind of one of the things that Go's doing to addressing that is they're making some kind of hard guarantees about how long garbage collection will take and how long garbage collection pauses will take. So what the plan is, and this is not 1.4, it's 1.4 plus, so I don't know exactly what that means. I assume that means they won't get it all done by 1.4. But no more than 10 milliseconds out of every 50 milliseconds will be spent in stop world garbage collection. The remaining 40 milliseconds, they will have a concurrent garbage collector running, I guess trying to get as much work done as they can. And then they have this concept of mutators, which is any thread, let's see if that's right in this statement, probably any Go routine other than the actual garbage collection Go routines. And some mutators will be asked to do some GC-related work, which I interpret that as meaning, assuming 10 out of 50 milliseconds isn't cutting it, your Go routines might be incrementally slowed down as they're asked to do more GC work. But I'm not sure if that's a correct interpretation. That's just my first pass at it. But, I mean, it sounds very convoluted, but at the end, I think you'll be able to say if you need a low latency, like Go program, they'll be able to make guarantees about pauses. And that's pretty awesome, because that's really hard to do. It's really hard to do in a garbage collected environment. And when you're doing, like, so many, like, microservices now, like, require, like, just that many more operations for something to complete. So if you have a distributed system and you need to make, like, 100 API calls, or maybe just 20 API calls, and those API calls, and this app actually was talked about in the last Go Meetup, but if like 9 out of 10 times those Go API calls are very fast, and you've got to make like 20 of them, probably going to get a slow one. And if the thing that's slowing you down is GC, you really have to get that, or GC pauses, you really have to get that number down if you want it to be down like in the 95th percentile of all requests through. Which, if you care about that sort of thing, matters. Yes. Anyway, so done with the garbage collection stuff because I'm not really smart enough to talk about it anyway. I thought this was really interesting. So, do you guys know? Does anyone here know how like Go slices are implemented versus arrays? What's the difference?
I can't remember. I've read.
Well.
We've all read it like 20 times.
Yeah, no one.
It doesn't. Yeah.
It doesn't really.
Does it not stick? Okay.
It's like every time.
Just a 3-word descriptor points to the array beginning of the slice, how much space is available in the rest of the array, and how much of it is actually used.
Right, I've got a CS question. Well, I don't know what kind of question it is. Isn't a word like a byte? Because if it's 3 words, would it be 60? I mean, I know it's a 64-bit descriptor.
2 bits at one point, 32 bits later.
So a word is the same as like size of a pointer.
Typically.
I wondered myself. Okay. So yeah, that is right. Basically, like slices, they're really just like. Most of the time in C, if you're like working with an array, you're working with like a pointer to the first element of the array. So if you want to do anything safely, you have to know how long the array is. So you need 2 things that you have to pass to every function. And Go arrays are rollable, so that like you have a little extra space, and you need more than that, it will reallocate the array and make it bigger. And those are your 3 words, which I didn't realize that words were pointers. So because of that, pointer arithmetic happens in Go.
I'm sorry.
Yeah.
I should have been more precise. Word is architecture dependent, is really what I was trying to say. It's the size of the element. It's typically the size of an int.
Okay.
But different minds differ on what word is.
Yeah. So, one of the interesting things is like Go tries to be a safe language, which means it's not going to allow you to access things like uninitialized memory or walk past the end of an array, and it doesn't allow pointer arithmetic. But you can't really do arrays without some sort of pointer arithmetic behind the scenes. And so Go implements pointer arithmetic, So when you try and access, like, some element of a slice, this is what it does. These are those, I'm using 2 of those 3 three words that he was talking about. You don't generally have to check the capacity when you index into a slice. That is a runtime check that Go inserts into every array access to make sure that it's safe. And if you access something out of bounds, you get a panic. And that has to be done at runtime, partly because of the fact that there's the capacity thing. Like, you could have an array that's conceptually only 10 elements long, it's got an allocated capacity of 20 elements, and it's illegal to access the 11th element, even though, like, it would work, but it would be like, I don't know, garbage. So they have to check it out at runtime. Arrays are a little different than slices in just that they're fixed size, which means the compiler knows how big they are, so you don't really need a header to store how big they are. At least that's the way I look at it. So when you access a value in an array, it basically gets compiled down to some pseudocode like that. And these are all like checks that are inserted by the compiler at runtime to make sure your code is safe. Occasionally, let's see if I got this. I do. So the compiler can be pretty smart. It doesn't always need to insert those bounds checks, and the reason these bounds checks are so kind of important is that is like a runtime behavior that slows down your code versus C. So if you want to get as close to the metal as possible, you don't really want bounds checking to be happening. But if you want your code to be correct and not, result in undefined behavior, you do want it to happen. Sometimes you can get the best of both worlds. So if you're using a sort of range access, the range operator in a for loop, Go can often elide, there's that my favorite word again, it can elide the bounds check. And if you look at the assembly that's generated from that, you won't see like a check and a panic index call, which is kind of nice. So built-in looping operators do actually give you higher performance in that case. Because the compiler knows, because it generated the code for the for loop, it knows that I is always valid. And also say the same thing, if you're working with an array, certain constant expressions, like you have a 10 element array and you want the third element, like you're never going to get an out of bounds situation on that. I did not actually test to see if the compiler optimizes that case, but it certainly could. So the other thing I mentioned is Go basically tries to so when Go's using interfaces, it tries to statically verify that that whatever you're passing to an interface implements that interface. It didn't work that very well, but that's what you get when you have compile time duck typing, or what they call structural typing. Sometimes in Go, you can actually check at runtime, though, to see if something implements some random interface, and Go doesn't really know ahead of time. And so it has to have all these reflection tables. Not reflection tables. It has to have, basically, they call them I tags, which are a lot like V tables, but in the header files, they call them I tables, because I guess they didn't want to call them V tables. And those help, and it uses those at runtime to find if something actually implements some other interface, and look up the appropriate method call to make when it actually calls close. And I kind of did some checking and looked at the assembly generated, and it looked like a few of those were. So when you do a type assertion, you're trying to extract the concrete type out of the reader, like an os.file. It actually has runtime code that does all that. It's called assert I2T. That's the little C function that it calls. And then I don't actually know what E stands for. I've wondered. I know I must be interface, T must be type. I don't know expression. But anyway, this is kind of this runtime stuff. It's an abstraction that you pay for at runtime, which is kind of getting to the point interface calls in Go are not necessarily going to be as fast as direct, I don't know if the right term would be method calls, but non-interface calls. But there's not a huge difference. They definitely do some caching of the info they look up, at least according to my reading they did. Excuse me. But there's two reasons this are important. One is you actually want it to be safe, so you don't just want to cast something to something else and then just let it blow up if it doesn't actually implement the interface. And the other is, since it actually has to look up the method in an I table, you actually need to do that work at runtime so you know which close function to call. Yeah, I said that already. See, I do that.
Any idea on the performance compared to like Java reflection, something like that?
I'm not sure actually, because there's also a little bit of a difference between reflection and like the vtable lookups or itable lookups.
More
But-
similar to tasking, like you said.
But I mean, it's basically I should find the way that it looks or the area where I saw where they explained like some pseudocode for what like an interface call actually looks like. But when you're making a method call in Go, like you define something on os.file, like a concrete type, like there's not any overhead to that. The os.file is just an implicit first argument. There's no more overhead than a function call. With an interface, like it basically has to, and any interface value in Go is actually two words. It's a type, a pointer to the type, and a pointer to the value. So you kind of imagine if you have to make a call like something foo.close on an interface value, you're going to have to go to the type, and then you're going to have to jump to the close method for that type, get a function pointer from there, and then actually that's what you call. So it's basically an extra pointer chase-ish. However that works out in practice, I'm not sure. So yeah, concurrency. So it's kind of interesting, like a lot of Go's runtime features are centered around like doing concurrency well. In fact, the reason why they did garbage collection was essentially because of concurrency. Like once you have like a bunch of closures floating around and like a bunch of like Go routines, it's really hard to statically reset the lifetime of a variable. Maybe not impossible, but it's pretty hard. So GC just makes all of that a lot easier, and that's why they did it that way. So the biggest feature of Go's concurrency method is, of course, like Go routines. Just because those really, they're conceptually just like a thread. But in practice, what's really, really awesome about them is they give you cheap threading or green threading. You can have, millions of Go routines. I checked that because I was like to make sure I'm not lying. Yeah, I made like 1 million Go routines on my system, and it used up a few gigabytes of memory because the Go routine stack is currently, they flip-flopped on this, it's about 4 kilobytes by default. I think they moved it from 4 to 8 and Go 1.2, but now it's back down again for some reason. Oh, really? And I know apparently in the current tip, I read this, it's set to 2 because they're trying to find bugs, but they're going to like move it back to 4.
I heard that they're going to do some like dynamic system analysis during to decide the stack size. That's why they switched from 4 to 8 and now down to 2. They're going to go
Yes.
through and check what the stack size would be for each one, determine the size from that.
That would be a good way to do it. Yeah, I assume without interface calls, you can reason about that a lot more. But that whole system's been changing quite a bit. But really their stack model of how they allocate data for Go routines is like key to being able to do concurrency in a Go style because it gives you, lightweight processes essentially, to use the Erlang term. And also Go has channels which are actually one of the most uninteresting parts about Go. Because Rob Pike actually had a quote, do I have it up here? No. Where he said that, channels are pretty boring, like they're basically a queue. Like, the interesting piece is when you get selective receive, so it's the select statement that is kind of the magic there, not necessarily the channel piece. So we'll talk about some of those. So most people stick with either like, a thread is an OS thread, or basically there's one, just one OS threads and everything is multiplexed onto it. Go kind of took the hard route, I guess, an end-to-end threading model. Although I did learn in Lambda Launch that Erlang now does something like this, but it's weird. They run like one user space scheduler per core, but then they do multiple cores. It's actually really interesting. They have some good ideas. Some of them just don't fit in the Go world, but they're still pretty cool. Like Erlang actually has this awesome thing where they can do GC in a much easier way because there's no shared data between their processes, as they call them, which are like Go routines, which makes it really easy because like you don't have to like scan the whole heap. You can do it all concurrently because it's all like local in the process, which is pretty sweet. because it is an end-to-end threading model, you have to do some things cooperatively because you can't just rely on like the kernel to schedule you out and schedule you in like correctly. So you can run into cases where you like start the scheduler and freeze the system, making those cases really hard to like reach, but they still happen occasionally. But part of how they make the end-to-end threading model work is, and this is really common in a lot of these implementations, all your blocking calls are converted into non-blocking calls, like under the hood. And they have a few different tricks for that. In the case of like network I/O on Linux, they're going to just use epoll or epoll is the system call you use. The subsystem in Go is called, I think, the net or maybe just polar. I don't know if they do file I/O asynchronously, but some syscalls are basically done in like a thread pool, which is separate from the Go max procs accounting. The same with CGO calls, because Go can't really reason about whether a CGO call is going to block or not, because that's opaque to it. So those are like basically run not in like the main Go routine set of threads. And that's why you can actually, even if you set Go max procs to 1, you'll still have more than one thread running most likely, because there's just a few things like that. And there's a term for this that no one ever really uses, but I think it's accurate. It's the green threads, like Java used to have back in the day. The really awesome thing about like this model is you get a reason about your code as if it's blocking. I know opinions differ on this, but like, I don't know, I thought I was going to tear all my hair out after I had to work with like a non-blocking system for like a year. I did a bunch of like twisted Python programming, and every time we converted something over to like a blocking style of code from like callback, like we fixed like 3 or 4 bugs because it was so much easier to see what was going on, what could go wrong, and how to make sure we handled it. Like we didn't know if we had to catch something, or if we had to do an error back, or what. So it's a lot easier to reason about, in my opinion. So everyone here probably knows what Go routines are, but one of the cool pieces of how they used to implement these was they used segmented stacks. So your stack was basically a linked list. And what that meant was they could do 2 things. They could start you out with a very little stack, which was the 4 kilobytes that we were discussing earlier. And you can have a lot of Go routines if they only have a 4 kilobyte stack. And then the other thing you do is it makes it really easy to grow. Like you just keep adding nodes onto that linked list. It's like a constant time operation, and it's like really easy. Unfortunately, one of the problems with linked lists is they don't have great what's the word? They don't have great characteristics with respect to caching. So if you have contiguous memory and you're not chasing pointers, that's often easier to work with. In Go's case, they had something called the hot split problem, which was that they'd end up with function calls in a tight loop, and that would be right on the stack splitting boundary, which meant that say you call the food function in a loop, it'd be like, oh, I'm going to call food. Let me get another stack frame. And in return, it'd be like, I'm done with that. I don't need that anymore. Oh, I'm going to call function food. Let me get another stack frame. And that was kind of a big performance problem. At least so they thought. And what they tried to do to fix it, which I think is really interesting, is essentially the same idea that they use with slices. Like Go's slices are kind of the standard global. Okay.
Everybody?
That was exciting. That was the most exciting thing that's happened so far. Go slices are really cool. It's Python, basically Python is work the same way. They're a very effective global data structure. They do that because every time you need to append to them, they essentially bulk allocate the data and then they do something like $1 size, which gives you this nice trick called an amortized constant time append, which basically means you can just keep growing them and not have it run into some crazy quadratically bad situation. Anyway, to jump back to stacks, what they did was they changed their stacks over to basically contiguous amounts of memory that they would grow on demand using some sort of factor of 2 or whatever. I'm sure they'll play around with that. And that gets rid of the hot split problem to some extent. And one really cool thing they did that I love talking about is that the thing is when they reallocate that data, they've got to copy it all over from the small array to the big array. But Go has all these pointers going on, and these pointers may point to data in the stack that is now removed or whatever. So now I was talking about this with the generator, with the copying GC, and how hard it is to fix up the pointers and move memory around. They're doing that with stacks, and you can definitely read more about it. There's some interesting invariants with stacks that make it easier in that case, but I haven't totally understood it all yet. Something along the lines of stack allocated pointers only going up and down, because that data doesn't exist yet. So that makes it a little easier for them. And yeah, they're scheduled onto OS threads. So, and you can do it on just one OS thread or lots. A lot of the times if you're doing network bound stuff in Go, you don't necessarily have to be running a lot of OS threads. In Go, you can have a program dealing with 10,000 concurrent connections, and you really only want probably as many threads as you have CPUs. I mean, it depends on the workload, but there's usually not much benefit to anything more than that. Sometimes it's better to have fewer because then you get better cache locality. So yeah, Go routines block.
Question about that.
Yeah.
One of the troubles I've seen with Go routines is they can jump between cores, and so it just totals your cache locality. Have you seen anything on the tip about them adding something like pinning a Go routine to a core?
I haven't seen anything about that. But while I was reading about the scheduler, I was diving through the source code, and I don't know if this is in the current Go 1.3 release, but the scheduler is a work stealing scheduler, but by default it will grab the routines that have been scheduled onto that core already, if it can, and it doesn't grab those. I shouldn't say core; that's probably the wrong term. It won't grab the routines from other threads unless it doesn't have any work to do, and it's in its local set of threads, or sorry, local queue of Go routines to run. So I assume that helps with the issue, but it might already be in Go 1.3. So yeah, Go routines block with air quotes because they look like they're blocking, and I guess depends on your definition of block, but generally when they block on I/O, they're yielding to the scheduler. Their stack gets swapped out, and something else runs on that thread. If you go through and look at the assembly to see how that actually happens, it's more compiler inserted magic. So Go actually will yield in I think 3 or 4 different types of conditions. So whenever you do I/O, basically that's a chance for the scheduler to swap you out. Yeah, that makes sense. Same with doing a selective receive or sending and receiving data on a channel, because you could block, and so the scheduler is going to swap you out. And that was, I think, initially how it goes, and just those. You could also be running a tight CPU boundary, and at this point, as long as you're calling a function within that loop, Go can generally swap out your Go routine for something else. But there are still some edge cases there, so if you want an infinite loop, bad things can still happen. But they're working, but it's pretty hard to get bad things to happen now. And I don't usually see that happening in a production environment. But it's one of the things that it inserts into the function calls is more stack, no context, which, as far as I could tell, is just does a couple things. It sees if it needs to give it more stack room, and also it's a chance to yield. Your network I/O, I already kind of went over that. They actually use a bunch of different things. If you strace those processes on Linux, you can see they're using everything from epull to select to regular queue text stuff. So they kind of got a fairly sophisticated polar event loop running, and yeah. And then they're just kind of when the I/O is done, they basically yield control back to that Go routine. And then syscalls. they kind of block, but I mean they do block, but they're usually running like a separate thread. So your main go routines aren't really blocked. They're more parked, I think is the technical term that they use. All right, so now it's going to get even more boring. So the Go scheduler, which like does all this, transparently making a million Go routine, or 4 hardware threads seem like a million Go routines. It does some pretty cool stuff. There's this crazy smart Russian guy who works on it, and any of his blog posts that you can read that Dmitry has done are probably worth reading. But there's 3 central data structures that you can read about. It's in the runtime header file. If you don't go from source, you just peek around at it. But it works with M, N, and P. And I'm pretty sure I know what M N. Those are match up. I don't know what N is. Sorry, it was kind of late at this point when I wrote this. I know what M and G are. P is a little more subtle, so I'm still trying to wrap my head around that. But you have, a data structure that's basically thread local stuff, represents one of your Go max procs. You have your Go routines, that's your G data structure. And then your P, the process context, is like a context somehow associated with like currently executing Go code as it's running on like a machine thread, I think. It's kind of strange. We're all learning this together. But it will actually use your machine thread, so M stands for machine, and you can to like Go and CGO calls. So a machine thread might be running something like a CGO call, but like it might not have a process context unless it's running a G, I think is the one it's like. And you get lots of like thread local storage, which isn't really allowed if you're like, writing Go code, but they use it like internally. And there's just a billion flags in here as you read through it. It's pretty interesting. Like there's just all kinds of hooks in there to say like, should the thread pause for garbage collection? Like, is the code in there panicking right now? How many CGO calls have been made? Which I don't even know why it tracks that, but it does. But it's basically, it's an OS thread. So the Go routine thing, this is where some of the runtime machinery for like panic and defer are implemented. So you've got like a stack of like defers running and all that fun stuff. It lets you know whether your Go routine is like blocked or parked or runnable or running, all that stuff. This is a really messy data structure because like almost all the features they implement in Go like have to be put in here. They have, if you guys haven't used it, Go has a really cool built-in race detector that's based on some internal Google code, I think, like a thread sanitizer library they use. Don't quote me on that. But when you build your code with like a dash race detector, and if there's any races that happen in your code, it will like bark on you and will know that it happened. And what's nice, more like potential races. You don't actually have to wait for 2 Go routines to like collide. It just notices that one value got written, and then maybe 10 seconds later, and that same value got read from, and that there was no synchronization event around that piece of code. And that's all, part of that implementation is actually in the race detector, in the Go routine race detector hooks. Yeah, this is one of the things P has. As you can see, I didn't know a ton about what P did. I tried to read the source code. But it does have a cool little like circular run queue of up to 256 Go routines, and then a bunch of other stuff. And that run queue is actually where it will pull Go routines from before reaching out to like another M, essentially. So it can actually maintain some level of locality there. So yeah, here's some more buzzwords about the scheduler. It is cooperative. Maybe it's like the Cliff Notes. Buzzwords maybe isn't a good word. It is cooperative, I guess. I mean, it is. Well, I mean, it's because the scheduler is working across multiple threads, OS threads, and certainly those are being scheduled in a preemptive way by like the kernel. And the people who did the kernel, they're really smart and they made really good schedulers. So we just have to, the Go folks just have to do the cooperative piece of when you have multiple Go routines running on one thread. It does do work stealing, which is a pretty interesting concept. Rather than everything pulling from like a global run queue of work to do, like there's not just like a giant list of these 500 Go routines need to be ran, and like every processor is like pulling up a Go routine. Like that doesn't happen. They all have their own like thread local run queues essentially, and they try and get work from those first, but if they run out of work, they basically randomly steal work from other run queues. And this seems like the sort of idea that wouldn't be like immediately obvious that this would be a good idea, but in practice, a lot of like schedulers end up implementing this sort of optimization. I now know apparently that the Erlang scheduler also does work stealing. Well, also the scheduler has to like work a lot. It basically has to know a lot about the other parts of the system. So it is integrated with the network poller. So like as it's running through, you can like read the algorithm. It's kind of interesting. It helps you know like what Go prefers. But Go basically tries to like find work to do in the local queue. Then it tries to steal work, I think, and then it tries to pull data from like a global queue. And then like step 4 is checking the net puller to see if anything's events have happened that like might have made I/O happen. So now a Go routine has to be woken up and ran. And if that doesn't happen, it just goes and blocks for a while. So it does an asynchronous net puller check, and then it does a synchronous one later on. And that's all in a piece of a little gem that I found called find runnable. But it helps you find where the next thing is. All kinds of interesting stuff. But that was where I saw that they actually, because when they pull from their global queue, they actually have to do some locking. Or they actually don't do locking, actually they do some atomic operations. But they're still incurring some overhead to accessing the shared structure with multiple threads. But before they pull from the global queue, when they just access their local queue, they don't have to do any sort of locking. So it's a lot faster. And I'm not positive exactly how work stealing integrates with that. Since that obviously that would be a case where another thread like looks at the data of that thread. Really dry throat today. Yeah, so select is actually really fun to learn about. Select is one of the pieces that comes from I don't know who came up with it originally, but it's present in like CSP, the course paper. I think it actually was part of, I'm not going to pronounce this name right, I think it was part of like just Straka's guarded statements. I'm sure I got that wrong. He's the go-to considered harmful guy. And what? Dijkstra. That's what happens when you read stuff and like never actually hear anybody say it.
It was also in an ADA.
Oh. I didn't know that. I know it's in Erlang as well. They have a selective receive. Hey, I'm also someone who thought it was like Euler's method for a long time. A long time before I learned it was like Euler, and they weren't supposed to call it Euler. So it happens when you go to school in southern Utah. There's no one to correct stuff like that for you.
Oh, that's the epitome of hyperbole.
What?
That's the epitome of hyperbole.
Isn't that hyperbole?
I'm thinking of hyperbole.
Thank you, Brian Regan.
All right. So yeah. So 2 cool things I want to touch on with Select. So one of the coolest things about Select is like if you're working with the blocking language and like you say make a database call, like that's really hard to like time out because like you call a function, how do you like make it stop running without like running in like another thread or whatever. And a lot of times you basically have to do something similar to Go, but they give you better tools for managing concurrency. So it's really easy to go make a blocking call. Well, spin off the Go routine that makes a blocking call and wait for its response on a channel. And you can add in like a timeout so that after like 1 second or 100 milliseconds, you go on your merry way because you don't want to wait that long for a response. You can throw in other things like an exit channel so that like if the whole program needs to abort while that thing is running, it can like receive a value there. It's just a really like versatile thing. Or is it versatile? I don't know. One actually cool thing is with the Go tip, they're actually working on rewriting more of the runtime in Go itself. And so you can actually go through right now and see how a lot of the select statement is currently implemented in Go, which is kind of interesting. It doesn't really look like the rest of the Go code you'd see like in the wild, but it is Go. It's very tightly integrated with like the C code. And I'm trying to remember, one other kind of interesting thing is select is pseudo-random. So if you have like 2 things you're waiting for in a loop, Like you're not always just gonna like wait for the first one and then not and deal with starvation and not ever get to the second one. That's all I remember off the top of my head. Is that it? Was almost all I had. I had one more bonus piece, something that I kind of blew my mind when I was learning about Go. So there's one check about in Go for like not type safety, like memory safety, that I assumed had to be implemented in the runtime, but it's not. And that is like nil pointer access. So when you dereference a nil pointer in Go, like usually in C land, if you do that, like segmentation violation, your process dumps core, you're dead. If you do that in Go, you get panic, which is like recoverable. And what's interesting is you think that, they actually have some sort of runtime overhead for like checking access to every single pointer. And they don't. If you strace one of those processes, and strace is like a Linux tool, system trace, kind of like dtrace for OS X, or I don't know what those people do. I could cry. But you actually see like these processes will get like a SIG-SEG-V, which is like a segmentation violation process, and it basically just gets handled like in the other signal, and the runtime does whatever it needs to like fix up the state of that particular Go routine and turn that into a panic, and up it goes. So the actual kind of the catching of that nil pointer dereference is doesn't really have runtime overhead, which is kind of interesting. Until it breaks, then you have runtime overhead, because defers cause like memory allocation and things like that. But that's all I have for tonight. So, that was nice and short. Any questions?
Yeah. I had a question. Read a blog post this week from Dave Cheney about it was a debug function. He used build tags, and in dev, the debug function logged stuff out, and in production it was just an empty function. Do you know if you're calling an empty function, does that incur any kind of performance penalty, or can you litter 1,000 debug things throughout your code?
I think you always have to look and check to see what decisions the optimizer made, but probably not. It probably doesn't. It probably just inlines it. Because there's two things that make that work. One is that Go actually has cross-package inlining, so some of that's done at link time, which is really cool. I think it's one of Dave Cheney's blog posts where he explores that a little bit. They do some weird stuff like save the source of the function, like they inline it at the call site, and then later if it needs to be done like inline in some other package, they inline it there. And so with an empty function, I'm pretty sure that's a no-brainer, and it's just going to inline it or off it away. And the other thing is there's a really cool flag you can pass when you're running go build. So if you do go build -gc flags equals -m, it will actually tell you what sort of optimization decisions the compiler is making. And it will be things like this thing is being inlined, this thing's escaping to the heap or being allocated on the stack, and also, I think there was one more thing, I can't remember what it was. But anyway, inlining and stack allocation.
The inlining only occurs when you're using a struct type. If you're using an interface, your host, it's going to make a call.
Yeah, and that's because it has to do it at runtime. Yeah, I mean, I assume it's one of those things where a sufficiently smart compiler could figure some of it out, but I assume it's probably not going to do anything like that. So if, for instance, you allocate an os.file, assign it to an IO reader, and maybe that's a bad example because I don't know if there's anything there that would get inlined. And then you make some sort of method or interface call. It's probably not going to be smart enough to know that you're really talking to an os.file at compile time. But I know there are some languages that do crazy stuff like that. And that's where you kind of get some of the benefits of JITting, because they can actually observe what the actual runtime type is and start to make more intelligent decisions about that. But Go seems like they're going to be a long ways away from implementing anything like that. But they've kind of bought themselves a lot of breathing room by having stack allocated value types, because that just out of the box makes a lot of things way faster. So you don't need like a crazy smart JIT to get you back to where you would be had you not decided to box everything. Yeah?
I have another question if no one else jumping in. Talking about stack traces. So even though panics make me feel like a terrible Go coder, they're also way easier to debug for me because it's telling me exactly where the error happened versus, okay, my error got returned all the way up the chain, and I'm like, oh crap, that error could have come from 100 places. And is there a good way to return a stack trace with an error, or if you have any good?
It's technically possible. I don't know if there's any good libraries. It wouldn't surprise me if the Space Monkey library, error handling library, did some of that. But there is, like, in the runtime package, you can programmatically get a stack trace. And I'm sure you could attach that to, like, an error type so that you could basically return, like, your own errors.new, and it would capture a stack trace at the time that it was constructed. So you could roll your own pretty easily. But yeah, I know I have the same problem. Sometimes by the time you get an error, it's something like IO error, and that happened, like, who knows where that happened, maybe it was on a log statement or whatever, like, it's kind of hard to debug. On an unrelated note, I decided log.fatal is usually a bad idea. Because it runs like an os.exit, and so, like, I don't think any of your defers run. So I decided not to use that one anymore. I would rather, like, log dot whatever and panic. Yeah.
Have you seen anyone that has success doing any kind of like stepping through a debugger with Go? I mean, coming from a language where I could just step through and pause threads and so forth, and then coming into Go, it's like, okay, yay, I get to do print statements again. In 15 years.
Yeah.
And so, have you seen anyone that's using like GDB with any degree of success? Because Rob Pike is like, he's kind of like, yeah, kind of did a bit like that.
Yeah, I fixed GDB a little bit, like, and it broke again shortly thereafter. Sorry, not GDB. They have a Python plugin that's shipped with Go that that basically is like a GDB plugin. And I fixed it to work with Go 1.2, but by that time, like, it was already broken in tip because they changed the runtime so much. But yeah, I've actually had pretty good success. Despite that, I've had good success running like GDB with Emacs, like source code level debugging with Go. But that being said, like, I don't really end up using it that much, but when I do use it, it seems to work pretty well. But that's just
you're using print statements as well.
probably like 95. Well, I don't know. It's probably like I use unit tests. It's like
Sure,
usually
sure.
I try and get it.
Yeah, but when like you're working with the unit test and it's just like, what is going on here? So you put it
Yeah,
in.
then I use like log statements, and I don't end up using GDB that often. Every once in a while, but I think that's partly just because so few other people use it. It's kind of like become like not the standard, but it works just fine. So, and Emacs integration is pretty good. Yeah.
In regards to the last question about errors, it took me a second to look it up, or panic messages. There's a package called Deep Error that lets you stack traces and chain errors together so that when they go up, you can follow where they came through. And I haven't used it, but it's a pretty small package and looks like it's pretty simple to use.
Cool, let's check it out.
Cool, let's check it out. Okay. Anything else or call it night? Yeah.
Is there a good place to find the compiler flags that are available to use? Because
I think they're
looked for
under
a few and
Go.
I've used them, but there's probably others that would be useful that I don't know about.
Yeah, I don't have a central place where I look. I mean, I usually just run random tools with -- help. Or if all else fails, it's in the source somewhere. Because it's not always obvious how certain flags get passed through to other phases. Like, I actually had that just today, like, where I was trying to pass, and this is really dumb, but it's the kind of stuff, like, I can't remember. I just wanted to run a specific test, like, under a package, and, like, you run, like, go test -- help. It's not really that helpful. And eventually, somehow, I got it to spit out the fact that I needed to run, like, I don't know, it was like dash test dash R, so I could give it like a regular expression instead of like test run. So good luck. Sure.
What are the best, like, this is completely off the runtime, but who are your favorite, I guess, blogs or people that are writing consistently about Go that you follow?